Good morning. So far, we discussed about the correlation, convolution, okay, and sampling theorem also, and how to reconstruct the original signal from the samples. Okay, so using sampling theorem, the original signal can be converted into sample, that is the discrete time signal. From this discrete time signal, how to get this original signal by using the reconstruction of the signal by reconstruction reconstruction of the signal, we will get the original signal, right? Now we are going to start the Laplace transforms and jet transforms. Okay, this is the last unit, Laplace transforms and jet transforms. The topics involved in this unit are, what are the topics involved in this unit? In Laplace transforms, so it is introduction about the Laplace transforms, concept of region of convergence, that is ROC for Laplace transforms. Next, constraints on ROC for various classes of signals. Next, properties of Laplace transforms, inverse Laplace transform, relation between Laplace transforms and Fourier transform of the signal. Okay, Laplace transform of certain signals using waveform synthesis, and some problems related to the above topics. In the same manner, for jet transforms also we are going to discuss about the concept of jet transform of a discrete sequence. Next, region of convergence in jet transform, constraints on ROC. ROC is the region of convergence for various classes of signals. Inverse jet transform, properties of jet transforms. Okay, distinction between Laplace, Fourier, and jet transforms, and some problems related to the above topics. Okay, okay. What is Laplace transform? So it is represented mathematically as the Laplace transform of the signal x of t is defined as Laplace transform of x of t is equal to x of s. Okay, where x of s is integral minus infinity to infinity x of t into e power minus st dt. This is nothing but the Laplace transform of the given signal x of t. So Laplace transform of x of t is x of s, which is mathematically represented as integral minus infinity to infinity x of t into e power minus st dt, right? Where x of t is a function of the independent variables s, which is a complex quantity. Here s is a complex quantity, that is s equal to, it is a combination of real and imaginary terms, that is sigma plus j omega. Here sigma and omega are real and imaginary quantities respectively. Okay, so here x of s is a function of the independent variable s, which is complex quantity, is a combination of real and imaginary quantities, which is represented as sigma plus j omega, where sigma and omega are real and imaginary quantities respectively. Here, x of t and x of s are called Laplace transform pairs. Laplace transform pair. X of t and x of t are Laplace transform pair. So Laplace transform is represented like this. So L of x of t is x of s. So coming to the unilateral Laplace transform. What is unilateral Laplace transform and what is bilateral? Here we have two types of Laplace transforms: unilateral Laplace transform and bilateral Laplace transform. Suppose if you take bilateral Laplace transform of x of t, that is Laplace transform of x of t is defined as x of s equal to integral minus infinity to infinity x of t into e power minus st dt is nothing but a bilateral Laplace transform, whereas it is varying from minus infinity to infinity. That's why it is bilateral Laplace transform. Coming to the unilateral Laplace transform, it is defined as Laplace transform of x of t is equal to x of s is equal to integral 0 to infinity x of t into e power minus st dt, or integral minus infinity to 0 x of t into e power minus st dt. These are unilateral Laplace transforms. Okay, so Laplace transform is defined as minus infinity, integral minus infinity to infinity x of t into e power minus st dt, right? Or it has two types: unilateral Laplace transform and bilateral Laplace transform. Unilateral Laplace transform is defined as integral minus infinity to 0 x of t into e power minus h dt, or integral 0 to infinity x of t into e power minus h dt. Coming to the bilateral Laplace transform, that is integral minus infinity to infinity x of t into e power minus h dt, right? So this is the definition of Laplace transform and types of Laplace transform. Now we are going to see the relation between Laplace transform and Fourier transform. Here we see the relation between Laplace transform and Fourier transform. So Fourier transform of a continuous time signal is a special case of Laplace transform. Okay, CT signal, continuous time. Fourier transform of CT signal is nothing but a special case of Laplace transform. So this is explained as the Laplace transform of x of t is equal to x of s is equal to integral minus infinity to infinity x of t into e power minus s t dt, right? Where s is a sigma plus j omega. Okay, sigma plus j omega is a complex variable. So replace s by sigma plus j omega. So x of sigma plus j omega is equal to integral minus infinity to infinity x of t into e power minus of sigma plus j omega into t dt. Okay. So what is the definition of the Fourier transform? Fourier transform of y of t is equal to integral minus infinity to infinity y of t e power minus j omega t dt, right? E power minus j omega t dt. Okay. So here this is nothing but Fourier transform of continuous time signal x of t into e power minus alpha t. So x of sigma plus j omega is equal to Fourier transform of x of t into e power minus j omega t if sigma is 0. In this one, if sigma is 0, this will become x of t into e power minus j omega t dt. This is nothing but Fourier transform. Fourier transform of x of t. If sigma equal to 0, in Laplace transform, sigma is 0, then it is nothing but Fourier transform. So that is Laplace transform of x of t is equal to Fourier transform of continuous time signal x of t into e power minus alpha t. Particularly, if sigma is 0, then s equal to j omega. Okay, then Laplace transform reduces to Fourier transform. That is Laplace transform at s equal to j omega is nothing but a Fourier transform of x of t. Okay, Laplace transform at s equal to j omega is nothing but Fourier transform of x of t. So referring to equation number 2, for convenience, for convergence of Laplace transform of x of t, okay, Fourier transform of x of t into e power minus alpha t must converge. Okay, so naturally for an arbitrary continuous time signal x of t, the signal x of t into e power minus alpha t may converge for only specific values of alpha. Therefore, x of s will converge for certain range of alpha, which will be referred as a region of convergence. Okay, this is called region of convergence. If ROC of region of convergence of Laplace transform includes imaginary axis, that is sigma equal to 0, then continuous time signal x of t is also Fourier transformable. Okay, this is about the relation between Fourier transform and Laplace transform. Then the existence of Laplace transform, that is a region of convergence. What is region of convergence? Uh, we have to see the region of what is the region of convergence. So Laplace transform of x of t is given by Laplace transform of x of t is equal to x of s is equal to integral minus integral 0 to infinity x of t into e power minus s t dt, right? So naturally Laplace transform will exist if integral 0 to infinity mod x of t into e power minus s t dt must be less than infinity. It means that it must be some finite value integrable and it must be some finite value. The sufficient condition is integral 0 to infinity mod x of t into e power minus s t dt must be less than infinity. Thus, for Laplace transform to exist, integral 0 to infinity mod x of t into e power minus s t dt must be finite, that is less than infinity. So what is region of convergence? The range of values of sigma for which the equation integral 0 to infinity mod of x of t into e power minus s t dt is finite is referred as a region of convergence or ROC. The range of values of sigma for which the condition or the equation integral 0 to infinity mod x of t into e power minus x t dt is finite, is referred as region of convergence. The concept of region of convergence can be thoroughly understood with the help of the following examples. Okay, so suppose if you take the simple example. Let x of t equal to e power minus at for t is greater than 0. Okay, e power minus at for t is greater than 0. Okay, let us take the two diagrams. If a is greater than 0, if a is greater than 0, it is exponentially decaying function. So it will be represented like this. If a is less than 0, it is exponentially growing function from amplitude 1. It is growing. So this is the diagramical representation of e power minus at for a is less than 0. Okay, now we will take the Laplace transform on both sides. Okay, then Laplace transform of x of t is equal to Laplace transform of e power minus at into u of t. U of t, if it is u of t, then it is varying from 0 to infinity. U of t equal to 1 for t is greater than or equal to 0. It is 0 for t is less than 0, right? So if it is u of t, then our limit values are varying from 0 to infinity only. So then x of s equal to integral 0 to infinity e power minus at into u of t value is 1 into e power minus s to dt Laplace transform formula. So here from 0 to infinity u of t value is 1. That's why it will become integral 0 to infinity e power minus at into e power minus s to dt. So take t as common, minus s common, minus t as common, it is s plus a. So integral 0 to infinity e power minus of s plus a into t into dt. Okay, then it will become e power minus of s plus a into t by minus of s plus a with the limits 0 infinity. So it is e power minus s plus a into infinity by minus s plus a plus or minus minus into minus plus e power minus of s plus a into 0 by s plus a, right? So let it be taken as term a and this is term b. So we'll simplify one by one. Term b, first of all we'll simplify term b. E power minus a plus a into 0, that is e power 0, that is 1 by s plus a. So it is finite for all values of s plus a. Coming to the first term, if s plus a is greater than 0, then s is greater than minus a. Okay, so if s plus a is greater than 0, then it will become s plus a e power minus of s plus a into infinity by minus of s plus a. So e power minus of s plus a into infinity is nothing but e power minus infinity, that is e power s plus a into infinity. 1 by e power s plus a into infinity, that will become e power infinity. E power infinity into minus of s plus a. So infinity, that is 1 by infinity is 0. If s plus a is greater than 0, then its value will become 0. Term a is finite. 0 means it is finite value. If s plus a is less than 0, then term a will become less than 0 means minus of s plus a. Before that minus will come. So it will become e power s plus a into infinity by s plus a. Okay. So e power infinity by s plus a. E power infinity is infinity. Infinity by s plus a is infinity. So if s plus a is less than 0, then its value will become infinite value. It should not be infinite. It should be some finite value. So if s plus a is greater than 0, we will get some finite value. So then term a will become finite if s plus a is greater than 0. Okay. So so that is minus s plus a is less than 0. S plus a is greater than 0. S plus a is greater than 0. That is the real part of s plus a must be greater than 0. It is term a plus term b. So if s plus a is greater than 0, its value is 0, and term by value is 1 by s plus a. So total it is 1 by s plus a, and real part of s plus a is greater than 0, or s is greater than minus a. In s, real part is sigma. Sigma is greater than minus a. Okay, Laplace transform e power minus a into u of t is equal to 1 by s plus a, but sigma is greater than minus a. Okay, so Laplace transform e power minus a into exists only sigma is greater than minus a. The sigma is greater than minus a is called region of convergence of x of s. Then we can draw the region of convergence for this problem. Then this which will be s plane. This is entire s plane consisting of real and imaginary parts. Real, and this is real part is sigma, and imaginary part is omega. This is like this. Okay, here s is greater than minus a. Okay, this is minus a and this part is minus a. So above the beyond minus a, this ROC will exist. Okay, this is ROC. This is ROC for this problem. It is greater than minus a, sigma is greater than minus a. So real part of S is greater than minus a. So this will be represented like this. Okay, right. Similarly, we'll take the next problem. That is problem number 2. So let when as x of t equal to e power minus 18 into u of minus t, right? E power minus 18 into u of minus t. So it is also diagrammatically represented like this. For a is greater than 0, for a is less than 0. If a is greater than 0, it is represented like this. And a is less than 0, it is represented like this. Like the above problem, like the previous problem, we will apply the Laplace transform on both sides. Laplace transform of x of t is equal to Laplace transform of e power minus 18 into minus of e power minus 18 into u of minus t. But u of minus t value is 1 from minus infinity to 0. Okay, from minus infinity to 0, u of minus t value is 1. Right? So here we will take the limits minus infinity to 0. Integral minus infinity to 0, u of minus t value is 1. That is e minus of e power minus 18 into e power minus s to t. So minus of e power minus t is common, s plus a into t dt. So minus of e power minus s plus a into t by minus of s plus a with limit 0 minus infinity. So simply we'll simplify this like the previous problem. So it will become e power minus s plus a into 0 by s plus a minus e power minus of s plus a into minus infinity by s plus a. So like the previous problem, it is also divided into two terms, term A and term B. We will simplify one by one term. If we take term A, this will become e power 0 by s plus a. It is equal to 1 by s plus a for all values of s plus a. For term B, if s plus a is greater than 0, then it will become e power s plus a into infinity, e power infinity, that is infinity. Infinity by s plus a, that is infinity. So we'll get infinite value if s plus a is greater than 0. Suppose for s, if s plus a is less than 0, then it will become e power minus of s plus a into minus into minus plus. So s plus a into minus infinity. This is e power minus infinity. Okay. E power minus infinity means 1 by e power infinity. 1 by e power infinity is 1 by infinity. 1 by infinity into s plus a is 1 by infinity. So 1 by infinity is 0. That is some finite value. So term B will become finite if the power of exponent is positive. That is for a plus s, okay, or s plus a is less than 0, we'll get some finite value. So it is equal to x of s equal to 1 by s plus a into 1 minus 0. So here s plus a is less than 0, that is s is less than a, s is less than minus a, or real part of s, that is sigma is less than minus a, that is the ROC. So its value is 1 by s plus a, and sigma is less than minus a. We'll draw the s plane like this. So this is a imaginary axis and real axis. So it is less than minus a. It is below minus a. ROC. Okay. Next, coming to the next problem. That is x of t is equal to e power minus 2t into u of t minus e power 2t into u of minus t. Okay. E power minus 2t into u of t minus e power 2t into u of minus t. Actually, this problem is a combination of the previous problems, problem number 1 and problem number 2. Combination of the previous problems 1 and 2. Okay, so here the first part is looking like problem number 1, and second part is looking like problem number 2. Okay, see, e power minus t into u of t is represented like this, and minus e power 2t into u of minus t is represented like this. So taking Laplace transform on both sides, Laplace transform of x of t is equal to Laplace transform of e power minus 2t into u of t minus e power 2t into u of minus t, right? So that is Laplace transform of e power minus 2t into u of t minus Laplace transform of e power plus 2t into u of minus t, right? So taking Laplace transform, so integral minus infinity infinity e power minus 2 into u of t into e power minus s t dt minus integral minus infinity infinity e power 2 into u of minus t into e power minus s t dt. U of t is varying from 0 to infinity. So here the limits are integral 0 to infinity e power minus of t into 2 plus s dt minus of u of minus t will vary from minus infinity to 0. So integral minus infinity to 0 e power 2 minus s into t dt. Or we can write this as minus of s plus 2 minus of s minus 2 into t, or this is a minus of s plus 2 into t, like that we can say, we can do it anyway. Okay, so it will become e power minus of 2 plus s into t by minus of 2 plus s with limit 0 infinity minus of e power of 2 minus s into t by 2 minus s with limit 0 minus infinity, right? So simply doing the problem 1 by s plus 2 with the sigma is greater than minus 2 for the first one solution, and for the first part term b part 1 by s minus 2 with the sigma is less than 2. Okay, so sigma is greater than minus 2 and sigma is less than 2, that is it is in between minus 2 to 2, sigma is in between minus 2 to 2. So the combined ROC of x of s is x of s equal to 1 by s plus 2 plus 1 by s minus 2. Okay, so with the ROC minus 2 is less than, sigma is less than 2. So first of all we will draw the ROC for sigma is greater than minus 2. So this is this part, this one first part. This is sigma is greater than minus 2. Then second part is sigma is less than 2. This is plus 2. Sigma is less than 2. It is below 2. So there is a overlapping from minus 2 to plus 2. This is the required ROC. Okay. By taking LCM, it will become 2s by s plus 2 into s minus 2. So this is so overlapping part is nothing but our ROC. Okay, from minus 2 to plus 2. Now we are going to see the poles and zeros are Laplace transforms. Okay, poles and zeros are Laplace transforms. So Laplace transform of x of t is equal to x of s equal to n of s by d of s. N of s is numerator polynomials of x of s, and d of s is a denominator polynomials of x of s. Okay, numerator polynomials of x of s by denominator polynomials of x of s. Okay, poles. What are poles? Poles are generally located as roots of denominator polynomials. Zeros are roots of numerator polynomials. So it can be represented mathematically as zeros are numerator polynomials, poles are denominator polynomials. So it is x of s, it is represented as x of s equal to s minus z1 into s minus z2 into s minus z3 by s minus p1 into s minus p2 into s minus p3 into s minus p4 and so on, right? So it will be represented by this s minus z1, s minus z2, s minus z3, s minus z4, like that, and s minus p1, s minus p2, s minus p3, s minus p4, like that. Okay, so here the zeros are z1, z2, z3, z4 up to zn. So poles are P1, P2, P3, P4 up to Pn, right? Suppose if we take the simple example, x of s equal to s into s plus 2 by s plus 5 into s plus 3. Here the zeros are z equal to zeros are at s is 0 and minus 2. Okay, and the poles are minus 5 and minus 3. Okay. Next, coming to the properties of region of convergence. Okay, properties of region of convergence. Properties of region of convergence. Here, ROC is useful in analysis of continuous time signals. Region of convergence is useful in analysis of continuous time signals. Some important properties of ROC are discussed here. So the first property is the ROC of X of S consists of strips parallel to j omega axis in complex variable plane, that is also called as S plane. Okay, the real the ROC of X of S consists of strips parallel to j omega axis. See, the ROS of X of S consists of strips parallel to j omega axis in complex variable plane are explained. This is so because ROC is dependent only on the real parts of S, that is sigma. ROC depends on real parts of S. Okay. Next point is the ROC does not contain any poles. So it does not contain any poles. Third one is if f of t is a time limited signal and is Laplace transformable, then its ROC will be entire S plane. S plane, entire S plane means this one, entire S plane. This is entire S plane. So delta of t is a time limited signal, that is it occurs at t equal to 0 only. Okay, these are 3 points. Then 4, 5, 6 points are also there. Okay, in the next class we will discuss about the remaining properties. Okay, with this I am concluding the today's class. Okay, thank you.